Hello and welcome to Calculus Lesson 8.4, Intersections of Lines in R2 and R3. So the blurb I have written at the top of the page is just something that you've probably thought and encountered again in various math courses. And that is the idea that when you have a certain number of variables you have to solve for, you need at least that many equations in order to solve. So for example, if you have two unknown variables you're trying to solve for, that means you need at least two equations. Usually two equations will give you the solution, but sometimes it's not guaranteed. You might have two equations, two unknowns, and it might still not give you a solution. So today we're going to investigate what it means to have a solution between equations of lines. And we're going to start off in R2, two-dimensional space. And in two-dimensional space, there are three possible cases. Okay, so again, R2 means two-dimensional space. All right, so go ahead, grab your ruler and sketch out three Cartesian coordinate systems, but only the first quadrant. I'm just going to sketch them here next to each other. All right, and label your axes as always. Okay, so in the case on the far left, there's three possible cases, like I keep saying. You've got two lines, and there's a couple of ways these lines can intersect. Imagine these pens are my lines. Either they're going to lay like this, so they have the same slope, they're parallel, and they will never intersect. Either like that, maybe something like this, they intersect at one point, or they are together, they are coincident. They have the same slope and exactly the same points. So we are going to sketch out those three scenarios. Okay, so the first one we looked at was that they are parallel and there is no solution. Okay, so something like that. Okay, the second case, okay, so let's just draw, how about we draw one line always the same? Let's draw the blue line always the same, so like that. Okay, so again, parallel, here we have intersect, and here we're going to have coincident. Now coincident, technically you wouldn't be able to see both colors here, but I'm going to draw them next to each other, even though they are technically superimposed, right? Because the superimposing them, you would only be able to see one color. All right, so those are my three cases. All right, so let's go ahead and label those. So the case on the left, this is parallel. The case in the middle, this is intersect. And the case on the right, we say that this is coincident. Okay, and I'm going to put a really short description underneath to determine how many solutions we have, right? Because this is what we're looking for. How many solutions? And is there a solution? Well, solution means what point or point satisfies both lines. And in the case where the lines are parallel, there is no point that satisfies both lines. So here we're going to say no solution. Okay, so for intersect, clearly there's one solution right there. Now, when they're coincident, this means that they quote-unquote intersect at every possible instance. So that means there are infinite solutions. And remember, that's still the case even if you have a restricted domain. All right, so let's go ahead and try an example. So example 1, determine the number of solutions. Okay, so for part A, we're going to be looking at the following two lines. So L1 is 4x minus 6y equals to minus 10. And L2 is 6x minus 9y is equal to minus 15. So when you look at these two equations, you have to use just problem-solving skills here. And with a lot of these problems, there isn't always a specific algorithm to solve it. So it's not as if you can always follow the same number of steps. Some of you might think of solving the question one way, some of you might think of solving it another way, while all of you at the same time are using the skills developed in this chapter, in this type of knowledge. So what we covered in chapters 7 and 8. Okay, so here, I know that this is the equation of a straight line in standard form. It's the scalar equation, right? I could easily rearrange each of these into y is equal to mx plus b form. And if you think of doing it like that, that's fine. I'm going to show you a different way, which some of you may have already noticed. I'm going to always label my equations. So I'm going to call the top one 1 and the bottom one 2. And what I notice is that if you look at the x coefficients, the y coefficients, and the constants, they're all related by the same factor. So if you take 4, well, how do you get from 4 to 6? I have to multiply by 1.5. How do I get from -6 to -9? I have to multiply by 1.5. How do I get from -10 to -15? Same factor of 1.5. So looked at this a different way, what I can do is factor out 1.5 or 3/2 from equation 2. Okay, so if I factor out 3/2, what am I going to be left with? Well, if I factor out 3/2 from 6, I'm going to be left with 4, and there's my x. Factor 3/2 from 9, I'm going to have 6, and there's your 6y. And on the right side, taking out 3/2, I'm going to be left with -10. Okay, so your 3/2 cancels on the left and right, leaving you with 4x minus 6y is equal to -10. Okay, so that is the same equation as 1. Since it's the same equation, it's the same line, that means you have an infinite number of solutions. So since it's the same line, therefore infinite solutions. Okay, so we always have to indicate how many solutions we have and why. All right, so something simple to get us started with in part A. Let's move on to part B. Okay. So in part B, I'll start on the new page. L1 is xy is equal to 1, 5 plus s -6, 8. And L2, xy is equal to 2, 1 plus t 9, -12. And in both of these cases, s, t are an element of the real numbers. Okay. So this time, instead of dealing with the scalar equation of a line, we have the vector equations of lines. And we have to see if these intersect, and if so, do they intersect only once, or do they intersect infinitely many times, or never at all? All right. Now, something that I know is that in both the outside cases, so parallel and coincident, for those two cases, the slope of the line is the same. And I'm going to use that knowledge to my advantage. So I can actually figure out the slope here. Now, if you have the equation in y equals mx plus b form, true, the slope is a lot easier to read, but you can figure out the slope easily from this form too. You have the direction vector, right? So here I have the direction vector m1, and on the bottom here I have the direction vector m2, right? And from the direction vector, we've seen in earlier videos, we can extract the slope. Okay, so the direction vector m1, so that's the slope direction vector for L1, so that's -6, 8. And the direction vector for 2 is 9, -12. Now with vectors, you know, and it's even written here, you're always given the x-coordinate first with a comma followed by the y-coordinate. So let's go with m1 first. So I have x and y. Now when you're dealing with slope, so the slope of line 1, I'm just going to call m1 without the vector symbol on top. Slope is rise over run. It's the change in the y values over the change in the x. And from what I see here, the change in the y is 8, and the change in the x is -6. Now 8 over -6, I can rewrite that as -4 over 3. So all I did was divide numerator and denominator by 2, and I just brought the minus sign to the top. That's fine. All right, so let's do the same thing for direction vector number 2. All right, so m2 is equal to y over x. So here's your x, there's your y. So minus 12 over 9. If I divide top and bottom by 3, I'm going to have minus 4 over 3. So there you go. It's the same slope. And the fact that it's the same slope means that these two lines are parallel. So the first thing I'm going to conclude is since L1 and L2 have the same slope, therefore L1 and L2 are either parallel or coincident. Okay, so I'm going to just bring up the previous page here again, just so we can look at this one more time. If they're parallel, there will be no points in common at all. And if they're coincident, if you even find one point on one line that also exists on the other line, you have proven that they are coincident. Okay, so we've got the two extreme cases here. Now, I know a point on each of the lines, and they're right here, given by these direction vectors. Right, so for L1, I know that the direction vector 1, 5 is going from the origin to the point 1, 5. And I know that a point on L2 is 2, 1. So all I need to do is take 2, 1 and plug it in for xy on L1, or take 1, 5 and plug it in for xy on L2. Either one is fine, so just pick whichever one you like. I'm going to go ahead and plug in 2, 1 into L1. So 2, 1 is a point. Oh, sorry, let me move that up. 2, 1 is a point on L2. Therefore, it may exist on L1. All right, so here we go. If 2, 1 is a point on L2, therefore it might exist on L1. That means that, therefore, the vector 2, 1 is a possible position vector to L1. Okay. So let's do this. So we are taking 2, 1, and we're plugging it into the original equation. So this one right here. Right, so take your 2, 1, stick it in over here. So that's equal to, I'll write it down and then I'll move the page up. Plus s minus 6 comma 8. There we go. So this is what we've got. Now, if that point, or in this case, the position vector, exists on the line, you're going to notice here, I'm going to eventually split this up into its x and y pieces. And if I can find that it's the same s value that matches the x value of 2 and the y value of 1 for both equations, that means that the point exists on the line. So here we go. I'm going to make two equations, one for the x and one for the y. So for the x, I've got 2 is equal to 1 minus 6s. And for the y, I've got 1 is equal to 5 plus 8s. All right, so here we go, my two equations. Let's go ahead and solve for s in both of these. So in the first one, I'm going to do 2 minus 1 is 1 is equal to minus 6s. And then s is equal to minus 1 over 6. Okay, the next one, I'm going to have 1 minus 5, that's negative 4, is equal to 8s. If I divide negative 4 by 8, I'm going to have minus 1 over 2. Okay, the s values are not the same, so therefore there are 0 solutions. So since the s values do not match, therefore the point 2, 1, which exists on L2 does not exist on L1, hence the lines are parallel. Right, so remember, they're parallel because we showed that the slopes are the same. And not only are the slopes the same, we also determined that there is not a single point, or in this case, this point is not on that line. And if they are coincident, then every single point that L2 has should also be on L1 and vice versa. So by showing that one point on L2 is not on L1, we have determined and therefore proved that these lines are not coincident, they are simply parallel. Okay, so that's our final answer. Okay, so there we go. Hopefully that's all right. So that is going to be the end of our exploration in two-dimensional space. Everything we do from now on will be in R3, three-dimensional space. Okay, so just to remind ourselves, I'm going to go back to this original page here. In R2, we had three possible cases: parallel, intersect, and coincident. So I'm going to grab my two pens here again. I'm going to show you something. In three-dimensional space, so you can have parallel, again, something like that. You can have intersection where they cross at one point, and you can have coincident. They are together, right? So in reality, it would be something like this. Okay, you wouldn't see the other one, but I stick them side by side just so you can see, right? So parallel, intersect, and coincident. Now, in three-dimensional space, what I can do is take one of these and change the angle. So all of a sudden, I've got two different angles, and yet they will never intersect. All right, so it doesn't matter how you do it. They might intersect, but they don't necessarily have to intersect. And they also don't have the same slope. So now we see a third option. Just because the two lines don't have the same slope doesn't mean they have to intersect. And that fourth case is called skew. Okay, so let's go ahead and investigate formally these four possible cases in R3. All right, so what I'm going to have you do once again is go ahead and draw four sets of Cartesian coordinate systems. This time they have to be the three-dimensional ones. So this one I'm actually going to do by hand, just without a ruler here. Okay, so we have something like this. All right. Let's do this. So just like before, I'm going to go ahead and draw two lines, one blue and one orange. We're going to start off this time with coincident. Okay, if two lines are coincident, just like in R2, that means they are together. So something like this. Of course, in reality, they're on top of each other, but there you go. Oh, and one thing I forgot to do was label my axes. So X is coming out of the page, Y is to the right, Z is up. X, Y, Z, X, Y, Z. Okay, much better. All right, now, so this first case is going to be coincident. Right, the next case, we're going to have, again, the simple intersection. So we'll draw blue the same way, and we're just going to draw orange at a different slope. Now, in this case, not only do they have different slopes, but they actually do touch. So intersect. Okay, case number 3, they are parallel. Okay, I'll draw blue a little different this time. So something like this. So far we've got the same cases as in R2. And there's that last case. Now imagine you've got this case where they intersect, and you take the blue line and you just move it up a little bit above the orange line, or you take the orange line and move it a bit to the right or the left compared to the blue line. They're no longer going to intersect, but they will still have different slopes. Okay, so in this case, I'm going to have a scenario that looks like this. So let's say this is my blue line. My orange line might have a different slope and go underneath it. Okay, something like that. And we call this last case skew. All right, now coincident, just like before, we have an infinite number of solutions. With intersect, there is the one solution. With parallel, you have no solutions. With skew, you also have no solutions. Now, there's two key words that I'm going to use to describe each of these, and those key words will become vital when we solve these types of problems and try to determine if the two lines that we're given are skew, parallel, intersect, or coincident. Okay? So using these two words, it will remind you what you have to prove in the problem and how many steps you have to show. For example, if our two lines are parallel and coincident, that's exactly what I have to show. That they are parallel, that'll be given by the direction vector, and they are coincident. So one point, at least that you can find, exists on the other line as well. Intersect. Now, when they intersect, these are distinct lines. So that means they're not the same line, and they intersect. Distinct would also imply that they have different direction vectors. If they're parallel, okay, so of course one word we're going to use to describe this is parallel, and distinct. Now in this case they do have the same direction vector, but they are two separate lines. And skew, here they are definitely not parallel, and they are distinct. All right, good. So let's go ahead and jump into our next example. Example 2. All right, determine the point of intersection, if any. All right. So line L1, x, y, z is equal to 5, 11, 2 plus s, 1, 5 minus 2. Line L2, x, y, z is equal to 1 minus 9, 9 plus t, 1, 5 minus 2. All right. So determine the point of intersection, if any. And we have to solve this in steps. Okay, so if there's a point of intersection, I mean, you're either looking at one of two cases. Either you're going to find that they are actually intersecting or they are coincident. You find one point, but in fact, they all intersect. Now, we have to use process of elimination here. Okay, so the first thing that I always like to look at is the direction vector. Okay, if I look at the direction vectors of each line, I can figure out if the two lines are parallel. And if they are parallel, well, I've already taken out 2 of the 4 possible options. And so if the direction vectors tell me that the two lines are parallel, they have the same slope, that means I'm only dealing with these 2 possible cases, coincident and parallel. So I've taken out these 2 cases. Likewise, if I find that the slopes and the direction vectors are not the same, or at least if the direction vectors are not scalar multiples of each other, that means that they can't be these 2 cases. So now you're dealing with the 2 cases of skew or intersect. Okay. So, and in the case of intersect, you actually have a point that you can solve for. In the case of skew, there isn't. So I don't know how many of you have played Guess Who when you were a kid, but this is kind of like that. Does the person wear glasses? Okay, are the lines parallel? If yes, put down the other ones. If no, put down those ones. All right. So we're going to inspect these direction vectors first. So M1 is going to be the direction vector for line L1. M2 will be the direction vector for line L2. Now, in this particular example, they are not only scalar multiples of each other, they are actually identical. Okay, so scalar multiples with the factor of 1. Okay, so since they have the same direction vector, therefore we have to conclude right away, and this has to be in your work, they are parallel. And you cannot just state that they're parallel. You got to say why. Because they're the same direction vector. Now, even if they were scalar multiples by a factor that is not 1, you can say they are the same slope since the direction vectors are scalar multiples of each other. Now, you figured out that they're parallel, so now we're looking at these 2 possible cases. So take out these 2. You're either coincident or parallel. All right. Now, if you're parallel, you're distinct. And if you're coincident, well, as it is described, it's coincident. All right. So that means you have lines, points that exist on both lines. Okay. So now we have to ask ourselves, are these lines coincident or are they distinct? All right. So if coincident, at least one point must be found to match. All right. Now, how do we do that? Well, we just did that in the previous example. Okay, so we know a point on L1 and we know a point on L2. A point on L1 is 5, 11, 2, and a point on L2 is 1 minus 9, 9. So all you need to do is take one of those points, plug it in the other equation, solve for your t values for each dimension of x, y, and z, and see if they match. Okay. So what I'm going to do here, I'm going to take the point 5, 11, 2 from L1. So the point from L1, 5, 11, 2, and I'm going to see if there is a t value such that the vector 5, 11, 2, I can set equal to x, y, and z. So that's equal to 1, minus 9, 9, plus t, 1, 5, minus 2. All right, so set up your three equations, one for each dimension, and let's see what we get here. So for x, I'm going to have 5 is equal to 1 plus t. For y, 11 equals minus 9 plus 5t. And for z, 2 is equal to 9 minus 2t. All right. So go ahead. If you get the same t value for all three dimensions, that means the point's on the other line, which means you have coincident. And if it doesn't match, even 1 point, that means they're distinct. So in the first case, 5 minus 1 is 4. I get t is equal to 4. So that's pretty simple. In the second case, I'm going to have 11 plus 9, so that's 20. Okay, so 20 is equal to 5t. So t is equal to 4. Looking good so far. Remember, it has to match for each dimension. You can't stop there. All right, last case, 2 minus 9 is negative 7 is equal to minus 2t. So the negatives cancel, and I have t is equal to 7 over 2, or 3.5. Doesn't work, right? So that's a problem. So since the t values do not match, 5, 11, 2 is on L1, but not L2. Hence, these two lines are parallel and distinct. Hence, and yeah, I know I've used hence twice in the same sentence, hence 0 solutions. All right, so in this particular case, I have this scenario, right? They're parallel and they're distinct. No solutions. So hopefully that is okay. All right, moving on to another example, example 3. Now, in example 2, we had to, well, actually, sorry, in example 2, we actually had to find the point of intersection as well. Sorry, let's actually go back and do that. Find the point of intersection. Well, there's no point of intersection, so we should actually formally state that. Therefore, there is no point of intersection. I suppose stating that there are 0 solutions would imply this as well, so I guess writing one or the other is fine. Okay, again, moving on to the next example, example 3. All right. Find point of intersection of L1 and L2. All right, L1 and L2. So L1, x, y, z is equal to 7, 2, minus 6, plus s, 2, 1, minus 3. And L2, x, y, z is equal to 3, 9, 13, plus t, 1, 5, 5. S, T are an element of the real numbers. I do believe I forgot to write that up here, so let me just fill that in quickly. S, T are an element of the real numbers. Okay, so same thing. We're looking for a point of intersection of L1 and L2. Now this one doesn't say if any. So that implies that there is actually a point of intersection. But we can verify this just to be sure. Okay, so look at the direction vectors. So we have the direction vector for L1 here, M1, and the direction vector for L2, M2. Now, looking at M1 and M2, just try to figure out if they're scalar multiples of each other. Clearly, they're not the same. To go from 2 to 1, I have to divide by 2. Sure. To go from 1 to 5, I have to multiply by 5. So definitely not the same factor already. So these two are not scalar multiples of each other. So I want to identify that right away. Since M1 does not equal K times M2, or you could actually formally write they are not scalar multiples of each other. Therefore, L1 and L2 are not parallel. Therefore, either intersect or are skew. All right, either they intersect or they're skew. Now, if I go back to my 4 possible cases in R3, I can see that if they intersect, I have at least one solution. And if they're skew, I have no solutions. So how do I usually find a point of intersection when dealing with vector equations? Well, I set x equal to x, y equal to y, and z equal to z. I can make an expression for each of those dimensions for both lines. And then I can determine whether or not, well, there is some solution there. So looking at L1, the equation for x for L1 will be x is equal to 7 plus 2s. Now looking at the equation for L2, x is going to be equal to 3 plus t. All right. Now, if you remember from before, the way in which we would solve these problems is, well, we would set the x dimensions equal to each other, hence we would get an equation with s and t. And then we would set the y equations equal to each other. We would get another expression with s and t, which would mean that we could solve for unique values of s and t. Now, that will always be the case. You'll always have unique values for s and t. The way in which you determine if a point that exists on L2 also exists on L1 is if the s and t values you extract from the first 2 dimensions that you use in your isolating of variables, if those same s and t values satisfy the z equations. And if you get the same z value using the t value you determined in L2 and the same z value using the s value you determined on L1, that means that you have found a point of intersection. So this is what we're going to do now. Let's look at L1 and L2 for y. And you don't just have to use x and y. You can use x and z. You can use y and z. It doesn't really matter. Okay, so for L1, we've got y is equal to 2 plus s. And for L2, we've got y is equal to 9 plus 5t. All right. So let's go ahead and make some equalities. So obviously, if there's a point of intersection, I set the x values equal to each other. And I set the y values equal to each other. 2 equations, 2 unknowns. I can solve this, most likely. All right, so I'm going to go ahead and solve for t from this equation right here. So I'm going to bring the 3 over. 7 minus 3 is 4. So I have 4 plus 2s is equal to t. And I'm going to call that equation 1. On this side, well, I don't really have to isolate for anything here, but I will combine the 9 and the 2. I'm going to have s is equal to, so 9 minus 2 is 7 plus 5t. Okay, so why don't we call that equation 2. And I'm going to take 1 and plug it in right here for t. Okay, so 1 into 2. So I'm going to have s is equal to 7 plus 5t. T is here. 4 plus 2s. So s is equal to 7 plus 5 times 4 is 20. 5 times 2 is 10. 7 plus 20 is 27 plus 10s. Oh, sorry, that should be a... Oh, no, that's right. Sorry, that's an s. Okay. All right. So we have 1s on the left, 10s on the right. 1 minus 10 is negative 9. So negative 9s is equal to 27. Divide left and right by negative 9. We have negative 3. Okay, so s is minus 3. Now take that S value and plug it back into equation 1. So we're going to have 4 plus 2 times S equals T, S being -3. So 4 minus 6 is equal to T. T is equal to -2. Okay, so these are the values of the parameters I've extracted using X and Y as my equations. Now, if you used Y and Z or X and Z instead, you would obtain different values for S and T. Just keep that in mind. And that's fine, as long as these S and T values also satisfy the Z dimension. So here we go. All right. So for L1, what do we have here? We have Z is equal to -6 minus 3S. And L2, we've got Z is equal to 13 plus 5T. So let's just check. So L1, Z is equal to -6 minus 3 times -3. Right, that's S. So -6, -3 times -3 is +9. So -6 plus 9, and we have 3. All right. Now, if I plug in for L2, I have Z is equal to 13 plus 5T. So T is -2. 13, 5 times -2, that's -10. So 13 minus 10, that is also 3. So it is the same value. Right? So by plugging in different values for S and T in my two different equations, I get the same Z value. That means that there is a point on L2 which also exists on L1, which also implies that the points are not skew. So I can take out that possibility. That means they intersect. Now I just have to find out what that point of intersection is, and that will be easy. I already know S and T values here, so I can take either one and plug it into whichever respective equation I'm dealing with here. So that's fully up to you. I'm going to go ahead and plug S into L1 just because it appears first. All right. So L1, I have X, Y, Z is equal to 7, 2 minus 6 plus S, which is -3, times 2, 1 minus 3. So I have a scalar multiple of a vector, so I'm going to take that value and I'm going to multiply it to each term inside. All right, so what do we get? We have 7, 2 minus 6 plus 2 times -3 is -6. -3 times 1 is -3. -3 times -3 is +9. Okay, so now you just have to add up the corresponding dimensions. 7 minus 6 is 1. 2 minus 3 is -1. -6 plus 9 is 3. So 1 minus 1, 3. That's the vector. Now, what is the point of intersection? So therefore, the point of intersection of L1 and L2 is 1 minus 1, 3. Remember, points have round brackets, vectors have square brackets. All right, there's one more thing I want to add to the solution just to make it thorough, and that is why we ended up crossing out that it's skew. Okay, so since the S and T values give the same value for Z from L1 and L2, therefore there is some point of intersection. So we should state that in some way right here. Okay, so since the S and T values from X and Y dimensions give the same Z value on L1 and L2. So there's the 3 and there's the 3 in your final answer again, right? So since they give the same Z value on L1 and L2, therefore there is a point of intersection between L1 and L2. So just something important that we should include in our final answer there. Okay, so that marks the end of example 3. We are officially 2/3 of the way through the lesson. We're going to go ahead and move on to example 4. All right, so here we go. Example 4, determine if these lines are skew. All right, so here we go. L1 and L2, X, Y, Z, X, Y, Z. Okay, so L1 we've got 5 minus 4 minus 2 plus T, 1, 2, 3. And L2 we have 2, 0, 1 plus T. Oh, sorry, I can't use T twice. Hang on. Let me grab my whiteout. Why don't we call the first one S? Okay. T, and we've got the direction vector 2 minus 1 minus 1. And we'll say S and T are an element of the real numbers. Okay, so there's our problem. Determine if they're skew. All right, so you already know what it means to be skew, but let's just go back and make sure. So if two lines are skew, that means we have no solutions. They do not have the same slope, nor are the direction vectors scalar multiples of each other, and they are distinct. That means they have no points in common with each other. So if we can prove that the direction vectors are not scalar multiples of each other or the same, and that there is no point that exists on one line that also exists on the other, therefore we have proven that the two lines are skew. All right, so let me just write down what I had just explained. So to prove that they are skew, I have to show that they are not parallel and no intersection. And I'll put in brackets, you have to prove both. All right, so first thing and the easiest thing that I like to look at is the direction vectors. Let's see if they are scalar multiples of each other. So here I've got M1, and here I've got M2. All right, so looking at this, to go from 1 to 2, I have to multiply by 2. To go from 2 to -1, I have to divide by -2. All right, so that's a bit of a problem. They are not scalar multiples of each other, so I have to identify that here. So since M1 does not equal a scalar multiple of M2, where K is an element of the real numbers, therefore L1 and L2 are not parallel. This is the easier one to prove, right? So we have to prove that they're not parallel and there's no intersection. This is the fast one. Okay. So now we have to show that there's no intersection by comparing the S and T values for all 3 dimensions. I'm going to write that down too. Now, show that there is no intersection by comparing S and T values for all 3 dimensions. All right, so same as before, we're going to look at our X equations, our Y equations, find S and T values for those 2 equations and 2 unknowns, and then see if they satisfy the Z equation as well. All right, so here we go. L1 for X. X is equal to 5 plus S. Okay, for L2, we're going to have X is equal to 2 plus 2T. All right, let's do Y. L1 and L2. So for L1, we've got -4 plus 2S, or rather Y is equal to -4 plus 2S. And for L2, Y is equal to 0 minus T. So you can just say Y is equal to minus T. All right, set the equations equal to each other. So X is equal to X, so 5 plus S is equal to 2 plus 2T. 5 minus 2 is 3. Okay, let's actually do this. 3 plus S is equal to 2T. I'm going to isolate for S because it looks easiest here. S is equal to 2T minus 3. Okay, so that's going to be a pretty handy equation. I'm going to call that equation 1. And going to the Y dimension, I'm going to have -4 plus 2s is equal to minus t. Now, if you want, you can multiply both sides by -1 and get that positive, or just go ahead and plug in the equation for s into here. Let's call that equation 2. All right, so we've got -4 plus 2s is equal to -t, s being 2t minus 3. So -4 plus 4t minus 6 is equal to -t. All right, -6 and -4, that makes -10. -10 plus 4t is equal to minus t. So bring this over. You're going to have -10 is equal to -1t minus 4t. That's -5t. So now you can see the negatives cancel each other out. That means t has to equal 2. Now take that t value and plug it in into equation number 1. S is equal to 2t minus 3. T is 2. 2 times 2 is 4, minus 3 is 1. So we obtain these s and t values. Again, if you decide to use the x and z dimensions or the y and z dimensions to get s and t values, they will not be the same. So just expect that. Now, let's check the z dimension. All right, so for L1, I have z is equal to, let's look at this, -2 plus 3s. And, okay, well, I'll do L2 afterwards. Let's just do this first, I guess. My s value is 1. So -2 plus 3 times 1. So -2 plus 3. 3 minus 2 is 1. Okay. And for L2, well, that's just right here. What do I have here? 1 minus t. 1 minus t. All right, so that's 1 minus t is 2. 1 minus 2 is -1. So they are not the same value. And notice if you make a really careless mistake here, you can easily obtain the same value and conclude the wrong answer here. So you do in fact have 1 and -1. They are not the same. Therefore, the lines do not intersect. So I'm going to state that here. Since the z values do not match for the given s and t values, therefore, the lines do not intersect. Now, we proved at the beginning that they are not parallel, and now we have proven that they do not intersect. And so our last statement, therefore, since the lines are not parallel and don't intersect, therefore they are skew. And this is what we've been asked to prove. So this is our final statement. Okay. So that is the end of example 4. Now the last example, this is probably going to be the most difficult one to visualize, and it's the most different from all the examples that we've done so far in this lesson. Now, interestingly enough, it's going to use concepts that we learned about back in chapter 7. So let's go ahead and do this. Example number 5. Determine the distance between the skew lines. Okay. So L1, we have x, y, z is equal to 5 minus 4 minus 2 plus s, 1, 2, 3. L2, x, y, z is equal to 2, 0, 1 plus t, 2 minus 1, 1. All right, so this is different. We're not looking for a point of intersection, if any. We are looking for distance between two lines. Now, the first thing I'm going to do is just sketch out two lines in a space. Okay, so let's say we have L1 and L2. Okay, so because they're skew, I know that they are not parallel and they don't intersect. So what I'm going to do is I'm going to take these two lines and place them on parallel planes. Now you could place them on planes that are not parallel, but that wouldn't help you get to the answer. In order to get to the answer here, we're going to place them on parallel planes. Okay, so for example, here is one plane, and here is another. Okay, so these two planes are parallel. It is very important that you draw a picture. This is not only a substantial way of showing your work for this kind of a question, but without it, you cannot hope to possibly understand how to answer this. All right. Now, a defining characteristic of planes is something called the normal. The normal is a vector that is perpendicular to a plane, and it tells us the orientation of that plane. Now, with planes, we're going to get more and more into planes in the last few sections of Chapter 8. And I think I did introduce this before, but with planes, instead of labeling like with lines, we have L1 and L2. Planes are labeled with the symbol pi. So I have pi 1 and pi 2. Now, the normal on pi 1, it either will go up and it's perpendicular to the plane, or it might go down and it's perpendicular. Either way, it's perpendicular to pi 1. So I'm just going to draw it up for now. The normal on pi 2, we can call that N2. Same idea, it's perpendicular to the plane. It might go down, it might go up. I'm just going to draw it going up for now. Now, since the planes are parallel, and I have to state that, therefore I can say that N1 is parallel to N2. Okay, so that's also an important thing to point out. Now, when I'm looking for the distance between these lines, it's important to note that since they are skew, the difference between 2 points, any 2 points that you pick, being the distance, will vary. So imagine I have, let me just use these two pens as an example. If I have these two lines, right, and they're skew, if I look, there's a very short distance in between the two lines. But if I want to pick an even further point, so if I pick the ends of the pens, for example, there's an even bigger distance there, okay? So what distance are we referring to here? We're referring to the shortest distance. Now, the shortest distance is the common perpendicular. Now, common perpendicular means that you draw a 90-degree angle to one line, you draw a 90-degree angle to the other line, and that is the shortest distance. Okay? So I have 90 degrees hitting this, I have 90 degrees hitting this. That is the common perpendicular. And what I want to do is find the distance, the length of this line right here. Once I figure out that, I'll have the answer. All right, now let's think about the information that we do know in this question. Well, I'm given the equations of the lines, so I know a direction vector on each line, hence I know a direction vector on each plane. And I know, given these position vectors on each line, or rather to each line, I know points on each line and therefore points on each plane. Now, L1 is up here and L2 is down here, so I might actually know these points. Let's say I have one point, okay, so this is on L2, and this is the point 2, 0, 1. I know another point on, L1, and it might be somewhere over here. It's not necessarily going to be on the exact other side of this common perpendicular. Okay, so that point is 5 minus 4 minus 2. I'm putting it a ways away because it's most likely not directly across from it. But what I do know is the vector going from one point to the other, I can determine. Let's see, I call that vector A. Now, vector A, I'm going to obtain by taking the vector that would normally go to this point. So that would be 5 minus 4 minus 2, and subtract the vector 2, 0, 1. All right, so I'm going to end up with one vector here. So 5 minus 2 is 3. Negative 4 minus 0 is negative 4. Negative 2 minus 1 is negative 3. So 3 minus 4 minus 3. That's my vector A. So how's that going to help us? Well, notice the normal vector n2. n2, well, that's going to be parallel to a vector here, which I'll just call n. Now, n is a normal vector, and what I do know is that n is parallel to this line segment D. So this symbol just means it's a line segment. If you recall from the study of projections, it's been a while since we did it, but from when we studied projections, looking at these two vectors, A and N, if I take the projection of A onto the vector N, I'll figure out the component of A that is in the same direction of N. And if I take its magnitude, I will get exactly the length of D. If I take the projection of A onto N, I'm going to get the vector starting from here going to the second, or rather in this case, the first line, L1. And if I take the magnitude of that vector, I will have the length of it, which is D. Now, the only thing here is, well, how do I figure out a normal vector, right, to that plane? All right, so let's figure this out. All right, so we've got D. D, we have established, it is the magnitude of the projection of vector A on vector N. All right, so if we recall, so it's been a while since we did this. If you don't remember the formula, that's okay. If you have A here in this spot, N in this spot, then the magnitude looks something like this. The magnitude of N dot A in the numerator divided by the magnitude of the normal vector in the denominator. Now again, A we just found, so that's good. We need N. And so a way in which to determine N, well, just find a vector that is, well, if I had N2, that would be great, but I don't have it. What I do know is I have these direction vectors. I have M1 and I have M2. Right, so M1 is a direction vector along L1 and M2 is a direction vector along L2. Now, those two, if I take the cross product of those two vectors, I will, by definition, get a vector that is perpendicular to both M1 and M2. Now, based on my picture, as long as I get a vector that is perpendicular to M2, or even M1, but in this case M2, I'm good to go. So I'm going to go ahead and take the cross product of these two direction vectors in order to obtain a vector which I can represent as N. So I have ijk, ijk. The first vector is the first direction vector that's going to go here. Sorry, let me go down again. So that's 1, 2, 3. 1, 2, 3, 1, 2, 3, and 2 minus 1, 1. 2 minus 1, 1. And I like to draw my lines. And I do the other direction in a different color. I notice some of you like to memorize the formula, and that's great. If you want to memorize it, that's completely fine. Just make sure that if you're memorizing it, you state the formula first, right? So for people who are doing what I'm doing, this is the way we show our work. So there has to also be a way to show your work if you're doing it the other method, and that is by stating the formula. Okay. So here we go. I know that my normal vector is going to have x, y, and z components. Now for the x component, that's where you look at the I values. That's 2 times 1, which is 2, minus negative 1 times 3, so that's negative 3. All right, for j, the y component, I have 3 times 2, which is 6, minus 1 times 1, which is 1. And for the z component, which is k, I have 1 times negative 1, minus 2 times 3, which is 6. Give me one sec, guys. Let me just double check these numbers. You know what? I wrote this a little sloppy. Let me cross this out and redo it again because I did not line things up properly. Let me do this one more time. I, J, K, I, J, K. And let's see, my first vector is 1, 2, 3, 1, 2, 3. And then I have 2, minus 1, 1, 2, minus 1, 1. I really want to make sure that I'm drawing these arrows through the right points, because if I don't, I'm not going to be using the right values in my calculation. Yeah, see? For K, it should be 2 times 2. All right, so that's looking a bit better. So let's do this. So for X, I have, let's just do this from scratch. 2 times 1 minus negative 1 times 3. And for Y, I have 3 times 2 minus 1 times 1. And for Z or K, I have 1 times negative 1 minus 2 times 2. All right, so what do we get? 2 times 1 is 2, minus, and that's going to be minus negative 3 or plus 3. We have 3 times 2, which is 6, minus 1 times 1, which is 1. 1 times negative 1 is negative 1, minus 2 times 2, that's 4. All right, much better. 2 plus 3 is 5. 6 minus 1 is 5. Negative 1 minus 4, that's negative 5. Interesting number that we're coming up with, or interesting vector. 5, 5 minus 5. All right, so that is our normal vector. Remember, this is a vector that is perpendicular to both M2 and M1. So by definition, if it's perpendicular to M2, then if I take the projection of A onto it, I will be able to get its magnitude, which is the length D. So taking the vector n and plugging it in over here, let's do that. All right, so magnitude of n dot A. Well, anyways, the dot product is a vector, a scalar. So 5, 5 minus 5, dotted with 3 minus 4 minus 3. So divided by magnitude of 5, 5 minus 5. So while the absolute value brackets are not necessarily important on top, the only way that it actually will have an effect is if you end up with a negative result, it'll automatically take the positive, right? Because distance can't be negative. That's why we have the absolute value symbols around a scalar quantity. So in the numerator, we're going to have the absolute value of 5 times 3. So right, take the sum of the products of each dimension. So 5 times 3 plus 5 times negative 4 plus negative 5 times negative 3 divided by, and when you take the magnitude of the bottom, that's a little different. You take the square root of the sum of the squares of each dimension. So 5 squared plus 5 squared plus negative 5 squared. All right, so on the top we have magnitude of 15 plus, well, let's just call that minus 20 plus 15 divided by square root of 25 plus 25 plus 25. Okay, so hopefully you see where this is going. 15 minus 20 plus 15. So 15 and 15 is 30. 30 minus 20 is 10. But absolute value of 10 is just 10 because it's positive already. So that divided by root 75. Okay, so at this point we can punch it in our calculator. So 10 divided by root 75, and we get 1.15 units approximately. So I'm using the IB rule of thumb here when I'm only putting 3 significant figures, but again, that depends on the specific instructions for the question. So the distance is approximately 1.15 units. Make sure you take your time to review this example. It is important, and it is quite different than the other examples. Of course, make sure you review those ones as well, but this one, definitely practice the picture. All right, so that is the end of lesson 8.4, intersections of lines in R2 and R3. Stay tuned next time for video 8.5.